All right, so our example involves a steady state temperature problem. So steady state temperature in a semi-infinite cylinder. So let's talk a little bit about the physical meaning of the problem before we set up the equation itself and the boundary conditions. It's a steady state temperature problem, meaning that the temperature, the dependence with respect to time of the temperature is going to be 0 in the object. But now the temperature is assumed to depend on two space coordinates, not just the radius rho, but also the height z. We still assume that it doesn't depend on the other angle, polar angle phi, but otherwise now we have the temperature dependence on two space variables. When you look at these problems, especially if they are formulated in physical terms, it's extremely important not to rush to solve it. You have to make sure you write your boundary conditions correctly, because I mean, if the boundary condition is wrong, the whole problem goes into a completely different direction, as you know already, including maybe having different integrals, right? I mean, different formulas for the Fourier coefficients and so on and so forth. We call this semi-infinite cylinder because we don't have an upper bound for z. So that means the height of the object is big enough so that for all practical purposes, we cannot specify essentially an upper bound of the object. We have a definite base when z equals 0, right? We have the bottom of the cylinder, but otherwise the height goes up indefinitely. And then the radius is equal to 1. So rho there is between 0 and 1. Now, what about the boundary conditions? Well, when I say the base temperature is kept at 1 degree, that means U of rho and 0, so when z equals 0, is going to be equal to 1. So that's one of the boundary conditions. By the way, this is going to be the non-homogeneous boundary condition, which, remember, you will deal with at the end in the process. When the exterior temperature is kept at 0 degree, that suggests essentially that we assume the heat exchange between the surface of the object and the exterior temperature according to the Newton law of cooling. So therefore, the boundary condition here comes from what we just discussed in the previous part. So in the previous part, just replace C with 1 in the boundary condition. And then that means from the Newton's law of cooling that the boundary condition will be U partial rho at 1T plus H U at 1T equals 0. So that is the one boundary condition, and that's the other one here. So again, if it's not clear, if you look at the previous notes, this is basically the Newton law of cooling, assuming 0 exterior temperature if the object has the radius c. So I simply replace c with 1 in my problem, and I got this boundary condition. So what about the PDE itself? Well, look at the Laplacian in cylindrical coordinates. If it depends on rho and z now, then the Laplacian of u equal to 0 is equivalent to u partial rho twice plus 1 over rho u partial rho plus u partial z twice equals 0. So this is the PDE to solve. Previously, we didn't have this because, again, we assumed dependence on rho and t, but now it depends on rho and z as well. And not on t because it's a steady state temperature. So the question is, in the long run, with these boundary conditions, what is the ultimate temperature distribution if you assume that in the long run it stabilizes in time? So if partial t with respect to u is partial t is 0. Okay, so let's move on with the separation of variables. We're going to go over all the steps in the problem here. And as with all separation of variables, of course, we're going to assume that u of rho z depends, it's a product of a function in rho and a function in z. And let's make suggestive notations, right? The portion in z, let's call it big Z of little z. And plug in the product form everywhere in the problem. So the PDE becomes R double prime of rho. I'm not going to say of rho anymore because it's implicitly understood. Big Z plus 1 over rho R prime big Z plus R Z double prime equal to 0. Boundary conditions become the following. The homogeneous one is the important one for now. So partial rho means R prime, but not of rho, but 1. Look carefully here. So differentiate with respect to rho, plug in 1 for rho. Sorry, this should be not T, this should be Z, because it doesn't depend on T anymore. Okay, so R prime of 1 plus H R of 1 equal to 0. Big Z of little z will be a common factor, but remember we're looking for non-trivial solutions. So then, therefore, this is the condition that we're going to deal with. And this is the one that leads to those mixed type of conditions in the formula sheet. So this is the homogeneous boundary condition. The non-homogeneous one, remember, we deal with at the end of the problem. Let's do the separation of variables. So we can factor z. We can factor z and then divide by z both sides. So this becomes r double prime plus 1 over rho r prime. Let's see. And let's divide by z and r as well. So divide by z and divide by r. So divided by r equals minus z double prime over big Z equals the separation constant, which, remember, anticipating already that we're going to end up with a Bessel equation, we can denote that separation constant by minus alpha squared. Okay, so the Sturmoville problem, okay, the equation in R, we already know the drill, right? We multiply by R, move it to the left, multiply by rho both sides to write it nicely. It's going to be a Bessel equation of order 0. Rho r equals 0 with the boundary condition given by r prime of 1 plus h r of 1 equals 0. That's the Sturmoville problem. And then the equation in Z minus cancels between them. So it will be big Z double prime minus alpha squared big Z equals 0 with no other conditions. So this will be solved for each eigenvalue found in the Sturmoville problem. All right, so pay attention now how you write the solutions of the Sturmoville problem. So now you look basically again at the equation itself. You recognize that this is an equation of a Bessel equation of order 0, right? So the solution is going to be R naught of alpha rho, excuse me, not R naught, J naught of alpha rho, right? The Bessel equation of the first kind. And the boundary condition, if we replace rho with 1, okay, so replace rho with 1 to plug it in here and differentiate, that's going to be alpha j naught prime of alpha plus h j naught of alpha equals 0. I hope this term is pretty clear here, right? I mean, if the solution for R is J naught of alpha rho, evaluating that solution at 1, when rho equals 1, that gives you J naught of alpha times H. Here, the reason you have the alpha popping out, again, is the chain rule, right? If I differentiate this and then replace rho with 1, when I differentiate J naught, I have alpha on the outside from the chain rule. And if you look again on the formula sheet and really pause and look it up, that mixed type of conditions, this is what you have there in the formula sheet when C equals 1, right? Because the radius is equal to 1. All right, so we know already that this has infinitely many roots. So the solutions of these, denote them by alpha j. So the roots of this condition are alpha j, with j equals 1, 2, and so on. So alpha j's will be the roots of the equation alpha j naught prime plus h j naught of alpha equals 0. These are your eigen alpha j squares, these are your eigenvalues. All right, so for each eigenvalue, so for each alpha j, solve the equation in Z. And now we label the solutions by j because there's infinitely many of them. So we're going to have Z double prime minus alpha j squared big Z equals 0. This is a second order ODE with constant coefficients, an old-fashioned one from the ordinary differential equation course. Just to make it clear, remember the characteristic equation is given by this. So you have two distinct roots, alpha j minus alpha j, and the solution of it is a linear combination of exponentials in Z. So big Z of little z will be some constant aj e to the alpha jz plus some constant bj e to the minus alpha j little z. So just a combination of exponentials because you have distinct real roots. Okay, so second order ODE with constant coefficients. Okay, so at this point, it's time to analyze a little bit this equation. Now there is, when I say that there is no extra condition on z, actually there is no numerical condition, but there is a boundedness condition. So again, remember, for the physical problem to make sense, the solution should be continuous and with finite limit at all points. So if I pick a point on the object, for everything to make sense, the temperature at that point should be an actual real number. And notice that because the domain of z is unbounded, so because z can go to up to infinity, so unbounded in z, that means aj must be 0. Otherwise, big Z of little z will be unbounded, which doesn't make sense from a physical perspective. So going back to the solution, we cannot allow it to be infinite at any point in the sense of taking the limit of it. And because alpha j is positive and there is no upper bound, this is where the semi-infinite cylinder comes into play. So because z can get to infinity, the solution should still be finite, should still have a finite limit, which means basically that you have an implicit boundary condition from the assumption that the solution should be bounded as a physical quantity. So therefore, aj must be 0. So with that in mind, that means z sub j of little z is some constant bj e to the minus alpha jz. One more time to review everything. You're going to have infinitely many eigenvalues. The corresponding solution of the Sturm-Liouville problem, let's label that with j as well. So rj of rho will be j naught of alpha j rho, right? So that's the solution of the Sturmoville problem in the form of a Bessel function with alpha j coming from this equation. For each j, right, so j is from 1, 2, and so on, you obtain a solution of the z equation, zj of little z, some constant bj e to the minus alpha jz. So this is the moment when you deal with the non-homogeneous condition after you use the superposition principle. So now you're looking for a solution, superposition principle. Now you look for a solution u of rho z in the form of a series from 1 to infinity. This constant bj e to the minus alpha jz times the Bessel function j naught alpha j rho. So on the next page, I'm going to do this in the same part here to not break the flow too much of the work. This is the moment now when we have to deal with the Fourier Bessel series. So let's impose the last condition, the non-homogeneous boundary conditions, which means that u of rho 0 should be 1. So we must have u of rho 0 equals 1. And if we plug that into the series format for the solution, so u of rho 0 on one hand should be summation from 1 to infinity bj e to the 0, because z is 0, j naught of alpha j rho equals 1. By the way, this is the function that stands for f of rho, right? When you use the formula for the Fourier coefficients. Okay, now I want you to take a look at the formula for the Fourier coefficients when alpha j come from, again, those conditions that can, so when alpha j is the root, or the roots of alpha j naught prime of alpha plus h j naught of alpha equals 0. So look at that formula and notice that bj is given by that integral in part b, except you replace c with 1 and the function with 1 as well. So on the top, you're going to have 2 alpha j squared. On the bottom, h squared plus alpha j squared. J naught of alpha j to the power 2. And the integral is from 0 to 1. Weight function is x. Well, I mean, I guess we could use just rho, right? Because the weight function is rho. That's a dummy variable anyway, so it doesn't matter as much, but let's just use rho to be consistent with the notation so far. So rho, the function itself, f of rho, is going to be 1, and then j naught of alpha j rho, d rho. Remember, when you evaluate these integrals, you always start by performing the substitution s equals alpha j rho. Do that all the time. So then, let's see, ds is alpha j d rho. Some change of variables. So change of the integration bounds, which are now from 0 to alpha j. Rho is s over alpha j, and this becomes j naught of s. And then d rho is going to be ds over alpha j. We can pull out 1 over alpha j squared. And we're left with sj naught. And remember, the antiderivative of sj naught is nothing but Sj1 of S. So this will be Sj1 of S evaluated between 0 and alpha j. Let's see, some cleanup here. Alpha j squared cancels. We have 2 over h squared plus alpha j squared, j naught of alpha j squared. And when I plug in alpha j for S, I have alpha j, j1 of alpha j. And this is the formula for the coefficient, for the Fourier coefficient. All right, so then the full solution of the boundary palette problem, going back to the series, so U of rho 0, the steady state temperature, will be the summation from 1 to infinity. Plug in the coefficient we just found. So it will be 2 alpha j, j1 of alpha j over h squared plus alpha j squared, j naught of alpha j to the power 2. The exponential e to the minus alpha j little z, and the Bessel function j naught alpha j rho. And that's the solution. So with that in mind, let's go over one more example with different boundary conditions. And don't forget, speed is not your friend on this. It's extremely important to go slow on your own to process this computation, because it's going to get easier, but you really have to sweat it out a little bit with paper and pencil. There's no other way, despite of what other people may think. Really, math is just at the root level. If you want to learn it, it's lots of paper and pencils. So stay tuned for the third part.